So we can start. I suppose it's time, and we'll start. Okay. So I just saw the assessment results. I'm quite happy with it. There were around some 40 people who. I request the participants to mute themselves. I request Bedi sir to have a check on that. Sir, kindly mute all the people who are there. Okay. Right. So, like 40 people have taken up the assessment, and the assessment, as I just checked up, many of you have done very well. So I'm very happy with the results. So I'll just let you know your marks personally. You'll get a message on that, and we'll also send a copy to the organizer, Bedi sir. So this fourth lecture will be on discussing the question and answers of assessment 1. Okay. So without wasting time, we'll just go ahead. Let the people who come and join by the course. So the first question was, what properties can be measured by a flow cytometer? So what properties of a cell can be measured by a flow cytometer? So the options given were size, granularity, fluorescent intensity, and all the above. Okay. Now this is a simple schematic representation of what happens in the flow cytometer. So we have cells which will pass through the flow cytometer. Okay. It goes in a single stream fashion by hydrodynamic focusing, and as they go in a single stream, it is hit by a laser light, okay, called the excitation light. So once this laser light hits the cell, two things happen. One, there will be scatter properties due to the light hitting the cell, and the light scatter happens. So that is one. So that is the scatter property happens. And the second is the fluorescence that is emitted from the stained cells. So I told you what is staining in flow cytometry. Staining is you are staining the cells with complementary antibodies tagged with fluorochrome. Okay. So whenever such stained cells pass across a laser beam, okay, the laser beam hits the cell, it excites the fluorochrome, and there will be fluorescence happening. So there will be scatter as well as fluorescence happening. Okay. Now this scatter again is of two types. One is forward scatter, which happens in the axis of light source, which will give you the idea about the size of the cell. Okay. And the second scatter is side scatter, which happens in perpendicular fashion. Okay. So that will give you an idea about the internal complexity of the cell. Okay. As I say internal complexity, I mean to say the internal granularity and cytoplasmic vacuums, anything. Okay. So by flow cytometry, we can able to study the size of the cell, the granularity of the cell, the fluorescent intensity of the cell. Okay, so the answer for the first question is all the above. Okay. Any doubts? So the answer is all the above. Fine. And most of you have done correctly. This particular question was answered. Almost everyone was right with this. So that's the one. So the answer for the first question is all the above. Now coming to the second course, this one, second question, everyone has got this right. What light source is used in most of the flow cytometers? It is the laser. Okay. Arc lamps were all used previously, but now it's all lasers which has been used. Now, third question was the forward scatter light is collected by, so whenever either let it be a scattered light. So as I said you, when the laser hits the cell, after hitting, there will be scattered light as well as the fluorescent light, which is getting emitted. Okay. Now, this light has to be collected, and we have detectors for collecting these particular light, scatter light and the fluorescent light. So now the question here is, forward scatter light is collected by which type of detectors? So we have seen that there are principally two types of detectors. One is photodiode and the other is photomultiplier tube. Okay, the third one, which is APD, avalanche photodiode, is a modification of photodiode where there will also be replication of electrons or multiplication of electrons. Okay, so now if you see forward scatter light, in what way it is different from the side scatter light and fluorescence is that this light is very strong because it is in the same axis of the laser light, correct? Because forward scatter is the light which is collected the same axis of the laser light. So it will be very strong. Okay, the intensity is very strong. So when you use a very sensitive detector like a like a photomultiplier tube, okay, what happens? The photomultiplier tube will get destroyed because already the light is very intense and strong. And when you use a very sensitive detector like photomultiplier tube, it will be destroyed. So the best suitable detector for high intensity strong light like forward scatter is photodiode, simple photodiode. Okay, for in case of side scatter and fluorescence, where the intensity of such light is very weak. Okay, because it is just a fraction of the laser light, correct? So side scatter, if you see, if you just do an experiment, if you just put a torch across a ball, okay, you see the predominant light will be in the forward direction, which will be hitting the wall. Only a small fraction of that light will be scattered all through, which is called the side scatter light as well as the fluorescent light. Okay, so now for such light, you need a very sensitive detector like a photomultiplier tube. You cannot use photodiode for side scatter light and fluorescent light because this is not sensitive. Okay, PMT is very sensitive and it is very helpful for collecting a side scatter light and fluorescence because there is a option of multiplication of the electrons inside the detector. Okay, so forward scatter light is collected by, since it's an high intensity strong signal, it is collected by photodiode. Okay, fluorescence and side scatter light will be collected by photomultiplier tube and avalanche photodiode, which is APD. Okay, so CCD camera, we don't use it in conventional flow cytometers. It is used only in imaging flow cytometers. So this is not the answer, and either these two are not the answer. The answer is photodiode. Okay, if you have any doubts during this discussion or you have a difference of opinion, let me know. Okay, am I audible? Let me check that first. Am I audible? Anyone?
Yes, sir.
Yes, sir.
Perfect. Fine, super. So if you have any doubts, you can raise your hands. Okay, thanks. See, let's make it very interactive. I want these lectures and these sessions to be more interactive so that we learn together. Okay, if you have a difference of opinion, if you want to put a hypothesis or something, we can discuss. Okay, let's make it more lively. Okay, thanks. So the fourth question, the advantage of flow cytometry technique over microscopy in cell analysis include all except. So again, most of you have got this right, but there were some people who had a different answer for this. The fault, maybe I can understand where it went wrong. I'll tell you. So flow cytometry, as I said you, by morphology, conventional morphology, by using a microscope or when you're studying the cells by microscope, as I said you, how many cells maximum you can study? If you sit for 1 hour, you can study around say 1000 cells or at the maximum 5000 cells, not beyond that. Okay, but with flow cytometry, I can study up to 1 lakh cells in 1 second. I can study up about 1000 to lakh cells in 1 second. So it is so fast, and the number of cells what I'm studying is huge. Whereas if you sit with a microscope, if I give you 1 hour, it's 1 hour time, you can maximum study about 5000 cells or 10,000 cells, not beyond that. Too, you cannot do the differential and so on. So you can just have a look at it. If I ask you to do a differential, you can't go beyond 500. Okay, and especially if I give you a very leukopenic hypocellular smear, then it is impossible for you to cover that. So flow cytometry can study large number of cells. Okay, and it is very rapid. So as I said, flow cytometry can analyze around 10,000 cells to 1 lakh cells in 1 second. So it is so fast and it can analyze so many cells. Okay, and when you're studying large number of cells, you have the chance or advantage of studying some rare cells also. So as I said, there are some circulating stem cells in your peripheral blood. But by conventional microscopy, there is very less chance of you encountering such cells in the morphology. Correct? So, but when you study lakhs and lakhs of cells, you can study those rare cells. You take grade 4 metastatic carcinoma, there are some malignant cells circulating in the blood. You cannot study it by microscopy, but you can do it by flow cytometry. So these are the advantages of flow cytometry. You can study rare cells, you can analyze large number of cells. It is very fast, rapid. Okay. One disadvantage is you cannot study the morphology of the cells. Okay, you cannot, by flow cytometry, you cannot see how the cell appears like. Some people have not taken up this answer because we discussed about imaging flow cytometry where we touched about morphology a bit. Okay, but that morphology is just a idea. It is not the exact morphology as we see in our conventional Romanowski stained smears. Okay, so since we discussed imaging flow cytometry in our first class as an advancement, some people thought even morphology can also be studied by flow cytometry, but it is not that great when compared to microscopy, which is gold standard. So the answer for this question is the advantage of flow cytometry technique over microscopy in cell analysis include all except it is rapid, it can analyze large number of cells and studying rare cells, but morphology is not that great when compared to microscopy. So the answer is morphology. Okay. Fifth question. So this everyone got it right. So particles must be in single cell suspension for flow cytometric analysis. Yes. Okay. When you have clumped cells or as a tissue bound together, cells bound together, you cannot study it by flow cytometry. So the first dictum is, for the first rule of thumb for a flow cytometric analysis is the cells has to be in single cell suspension. Okay. So the answer is yes. It has to be in single cell suspension for flow cytometric analysis. Sixth question. All the below samples shall be accepted for flow cytometric analysis except. So you apply the same law here. So of all the 4 options given, where all you can make the cells in single cell suspension. If you take bone marrow aspirate, the cells are already in single cell suspension, which means like they are in scattered single fashion. So you can study bone marrow aspirates effectively as the peripheral blood. Then if you see body fluids, again cells are all in single fashion. Okay, so you can study cells in body fluids also. If you take fresh tissue in RPMI, see, as a tissue you cannot study, but a processing step before doing flow cytometry called tissue dissociation or desiccation. Okay, where you subject the tissue to mechanical teasing or desiccation by some proteinase or protein digesting chemicals. Okay, when you subject the tissue to that, what happens? The tissue will then get disintegrated into single cells, and you can harvest those single cells and you can study it by flow cytometry. Okay, so even fresh tissues in RPMI can be studied by flow cytometry. Remember, fresh tissue in formalin is tough. If you put the tissue in formalin, then doing flow cytometry becomes difficult. But if you have fresh tissue in RPMI medium, you can desiccate them, you can dissociate them into single cell suspension by mechanical teasing or by using chemicals, and then you can, with that single cell suspension, you can do flow cytometry. So even fresh tissue in RPMA can be used for flow cytometry as bone marrow aspirate and body fluid. Paraffin tissue block, there is no chance like you can make a single cell suspension with this. Correct? Already the tissue has been fixed, it has been subjected to multiple chemicals, it has been dehydrated, so and so, and now you have already embedded in wax. And in such a tissue, you can take the DNA out, but you can't make the cells in toto as single cells. So the answer for this question is you cannot use paraffin tissue blocks for flow cytometric analysis. Okay, but you can use this for DNA, genetic studies. That's different. Molecular studies. Okay. So the purpose of the fluidic system in a flow cytometry is, so we, during a second lecture, we saw about fluidics. Okay. The basic purpose of fluidics is hydrodynamic focusing. What is that? So we have a sample which is injected into the sample core. Okay. And on or surrounding the sample core, we have a faster moving sheet fluid. Okay. When the sheet fluid comes to the narrowing area of the flow cell, okay, when the sheath fluid comes to the narrowing area of the flow cell, the velocity increases, and these randomly arranged cells will be made to pass through a single stream fashion or a single file pattern, which is called hydrodynamic focusing. Okay, so the principle or the purpose of fluidic system in a flow cytometer is to make the cells to pass in a single file, which is called hydrodynamic focusing. Okay, we saw this in the second lecture, right? So fluidics has nothing to do with collection of scattered light, which will be done by the detectors. It has nothing to do with enhancing the fluorescent emission. Okay, it has nothing to do with fluorescence emission. And similarly, it has nothing to do with excitation of fluorochromes, because it is basically done by the laser. Okay, so the answer is to make the cells to pass in single file pattern, which is called hydrodynamic focusing, for hydrodynamic focusing. Okay. Okay, now see the questions which I have highlighted in red is like questions where relatively many people have made mistake. Okay, so the questions what we saw till now, most of you have got it right. But this question, say like some 20 to 30% people have made mistake in this particular question. So the question here is a wider sample core decreases the resolution, and I'm asking you whether it's true or false, yes or no. What is this wider sample core? So this is the layout of a fluidics of a flow cytometer. Second lecture we saw this, right? So this is the layout of a fluidics of a flow cytometer. So we have the sheath fluid. You know what is the purpose of sheath fluid? We just saw in the previous image also. So this is the sheath fluid. This is the sample tube, and this is the flow cell. So you have pressure regulating the sheath fluid tank as well as the sample tube. So when you exert pressure here, what happens? The sheath fluid will rise up through this tube and flows into the flow cell. Similarly, when you exert pressure in the sample tube, the sample will rise up and it will fall in the flow cell. Okay, so this should happen simultaneously. Now, this particular sheath fluid pressure is constant. That is, you cannot adjust it when you are doing an analysis or when you are acquiring the sample. Okay, whereas you can able to adjust the sample pressure regulator in which the sample is being sent into the flow cell. So if you increase the sample pressure, more sample will flow into the flow cell. If you decrease the sample pressure, less volume of sample will go into the flow cell. Okay, so now this is constant. You can regulate this. So what happens when you increase the sample pressure? So when you increase the sample pressure, more volume of sample will go to the flow cell, correct? So when larger volume of sample goes into the flow cell, what happens? The sample core increases, correct? See, when you put smaller or low sample pressure, the flow of sample into the flow cell will be like this, as a thin stream. Okay, I request the participants to mute themselves, please. So when you increase the sample pressure, say this is low sample pressure, this is medium sample pressure, and this is high sample pressure. When you further increase the sample pressure, what happens? The amount of volume of sample which is delivered into the flow cell will be more, and the sample core or the thickness, the volume of sample which is going inside the flow cell is more, and the sample core increases. Okay, now when the sample core increases because of high sample pressure, what happens? The facade cells, when they go through the flow cell, since the sample pressure is high and higher volume of sample is getting into the flow cell, there is increased chances that 2 or 3 cells can pass at a time. Okay, so which are called as doublets or triplets. Okay, but when you acquire the sample in a low pressure mode, what happens? You get a very low volume of blood flowing into the flow cell. So the facade cells will be effectively hydrodynamically focused by the sheath fluid, and the cells will be delivered in a beautiful single file fashion. So you also get a very tight core. Okay, so when you increase the sample pressure, what happens? The sample core, the thickness of that sample core here, this thickness increases, sample core thickness increases, and there is increased chances of 2 or 3 cells going at a time as compared to single file pattern when you use a low sample pressure, which is desired. Okay, so when 2 or 3 cells passes at a given time and it interrogates the laser beam at a given time, what happens? You cannot study the cell completely and you get false increased signals. Okay, so that is the problem with wider core. So your resolution goes down. But in case if you study the sample in low pressure mode, okay, the cells will be neatly passed in a single file pattern and the resolution will be very good. Okay, so the point here is when you increase the sample pressure, the sample core gets increased and there is increased chances of doublets and triplets and your resolution goes down. Okay, so that is the reason behind this question. And when you're doing a very important assay, high resolution assay like ploidy analysis, this is very important in what sample flow rate you are doing the analysis or acquisition. When you do it in a low sample pressure mode, the core is very tight or thin, sample core is very tight or thin, and you get beautiful resolution like this. G0, G1, this is S phase, and then G2, M phase. But when you acquire sample in a hurry with a high sample pressure mode, the sample core thickness increases and then the resolution goes down. Now you see there is G0, G1, G2, M, but you don't see that clear separation of S phase in between them. So the resolution has gone down. Okay. So that is a very important thing. So, but if you're doing a qualitative experiment like immunophenotyping, you can acquire the sample in medium sample pressure mode or high pressure sample pressure mode. It doesn't affect your data much. But when you're doing an high resolution experiment like ploidy analysis, it is very important you acquire the samples in low pressure mode, low sample pressure mode. Okay. Now coming back to the question, a wider sample core, okay, which happens when you are acquiring the sample in high sample pressure mode, decreases resolution. Yes, true, correct. So yes, it of course decreases your resolution. Any doubts? There is some doubts. What is the meaning of resolution here? Okay, now what is resolution is? Resolution is separation. Separation in the sense, now this is what I meant by resolution. See, this is what you see here. This is G0, G1. This is G2 M phase. And you see the separation. Resolution is separation and clearly identifying the populations. Okay. So that is what resolution is all about. So clearly identifying the population and discriminating the signal from noise, and that is called resolution. Here the resolution is very poor because you cannot discriminate the G0, G1 from G2 M phase effectively. In fact, your S phase, which is trailing between the G0, G1, G2 M phase, is not seen here. So that is what resolution means. Clear? Is that clear, Dr. Pallavi? Okay.
Yes, sir. Thank you.
Fine. Perfect. So this one we answered. Let's go for the next question. So light scattered in the same direction or axis of the laser beam is called, this one everyone has got right. So this is called, so this is a light source. The scatter which happens in the same direction of the light source is called forward scatter, which gives you an idea about the size of the cell. And the scatter which happens in the 90-degree or a perpendicular fashion is called side scatter, which will give you an idea about the internal complexity, which includes granularity, vacuolations, cytoplasmic foldings, etc. Okay. So the light beam in the same direction or axis of the laser beam is called forward scatter. Okay. This is another example. Okay. So forward scatter gives you about idea about the size of the cell, and it happens in the same direction of the light source, which is the laser light source. The answer is forward scatter. FSC is proportional to, we just now saw, it is proportional to the size of the cell. Okay. Question 11. So again, this one, the same question what we discussed, same concept. A high flow rate can be used when performing experiments or assays that need high resolution like ploidy analysis. No, you cannot. Simply because of the reason what we discussed. When you want to do a high resolution experiment like ploidy analysis, where the separation between the populations are very tight, you should not use high flow rate. You should not use high sample pressure. Okay. So the answer is no. Coming to the next question, light scatter collected at 90 degrees to the laser beam is called side scatter. And it gives you an idea about the granularity, internal complexity, vacuolation, so and so. So this is what. So side scatter is increased. Sorry, there's some mistake. Side scatter is increased by dash of the cell. It is increased by granularity of the cell, vacuolations of the cell, cytoplasmic inclusions of the cell. So the answer is all the above. Okay. Next question. So question number 14. Any doubts till now? No doubts. Okay. Which of the statement is false regarding fluorescence? So before we go into fluorescence, is there a question?
Yes, sir, I have a question.
Yeah,
Sir, can
is
you
this Dr.
enumerate the
Your voice is not clear, Dr. Pallavi.
Okay, sir.
Yeah, please. Anyone? Yeah, who wants to ask a question? Like, you please let me know. Sorry. Yeah. What's the question? You can just put it in the chat box. I would love to take. Okay. Okay. Let me move on. If just give your question in the chat box. Okay. So, which of the statement is false regarding fluorescence? The excitation. Before we go into this question, let's just revise the fluorescence. Okay. So, please enumerate the low resolution assays again. Okay. So, low resolution assays. One is ploidy analysis. The other is when you're doing an RBC analysis. Okay, where there is no separation between the negative or a very tight separation between the different populations. Those are all low resolution assays. See, especially when you're doing some quantitative assays, those are all some high resolution assays. So you're asking enumerate the low resolution. Low resolution is any qualitative assays you do is low resolution assays. Immunophenotyping, leukemia, lymphoma. Okay, so those are all low resolution assays because though you acquire the sample in high sample pressure mode or in a the data is not going to get so much affected. But when you're doing ploidy analysis and stem cell enumeration, so very important assays. Okay, in such cases, you need to acquire the sample in a low pressure mode so that you have very high resolution of the data. Okay. Right. So before this question, let's revise fluorescence and then get back to that. Okay. So fluorescence is a property of a molecule when excited by a light of higher energy. Okay, it absorbs it. It goes for an excited state, and then it comes to the ground state by releasing energy in form of light called fluorescence or emitted light. Okay, so this is called fluorescence. Okay, I repeat, fluorescence is a property of a molecule. When it is excited by a light, it absorbs it, goes to an excited state, then it comes back to the ground state, okay, by releasing energy in form of emitted light, which is called fluorescence. Okay, now there are certain things you need to observe here. The emitted light, okay, the emitted light, in this case, the excitation light is violet in color, the emitted light is blue in color, correct? So the emitted light, the blue color, is of lower energy compared to that of the excitation light, which is violet color. Okay, see, the emitted light is blue in color, which is of lower energy compared to this excitation light, which is violet color. And you also need to know it is of the emitted light is of longer wavelength compared to the excitation light, which is shorter wavelength. Okay, so that those things you need to remember. Okay, now let me show you that. See, so the light, this is excitation light. It goes for an excited state, stays there for some time, then it decays. Then it comes back to the ground state by releasing energy in form of emitted light or fluorescence, which is always of lower energy compared to the excitation light. Okay, see, when the energy is lower, it has a longer wavelength. The wavelength there is shorter, whereas the emitted blue light is of longer wavelength. You need to know this. Okay, now some extra points about this excitation and emission light. The excitation, the range of wavelength, okay, the range of light wavelength which can excite this fluorochrome is called excitation spectrum. For example, now this is a FITC fluorochrome. Okay, now a light of wavelength between 400 to 525 can excite this particular fluorochrome to go to an excited state. So such a range is called excitation spectrum. But if you excite it with one particular wavelength, say 488 nanometer, which is that of a blue laser, okay, the excitation will be maximum, or the absorption will be maximum. Okay, now what is the advantage of exciting the fluorochrome in that one particular wavelength is when you excite in that particular wavelength, the absorption is maximum. Since the absorption is maximum, the emission will be very strong. Okay, so the range of wavelength which can excite this fluorochrome is called excitation spectrum, and that one particular wavelength which can effectively excite this fluorochrome where the absorption is maximum and emission is also bright is called excitation maximum. Okay, excitation max. Okay, now coming to the emission. Now we just discussed about excitation. Now coming to the emission. Now similarly, the light which is released when the fluorochrome is coming to the ground state. Okay, this particular blue light. Okay, this is called emission light. Okay, now this emission light is not of one particular wavelength. It is again a spectrum. It's a range. It can range from 500 to 625. Okay, this is called emission spectrum. Okay, spectrum means range. Okay, but if you see the maximum emitted light will be in one particular wavelength. In this case, it is 525. That is called as emission maximum. Okay, so you know what is excitation spectrum, excitation maximum. You also know what is emission spectrum and emission maximum. Clear? So this is called excitation because these all will come into play when you are selecting the fluorochromes. That's why I'm just stressing it upon again. Okay, now see, this is a blue light. It gets absorbed. Fluorochrome goes on an excited state. Then it comes to the ground state by releasing a light of lower energy and longer wavelength, which is green color. Okay, so this one we just saw in our third lecture, correct? In fluorescence and fluorochromes. So this is the visible spectrum of light, and here we see this VIBGYOR from violet to red, where violet has the light of higher energy and red has the light of lower energy. So violet has shorter wavelength and red has longer wavelength. So whenever you are exciting a fluorochrome, you can excite with a light of higher energy or a shorter wavelength, and the emitted light will be of light of lower energy and longer wavelength. So when you use a violet laser, the emitted light from the fluorochrome can be blue, green, yellow, orange, or red. If you use a blue laser, the emitted light will be, when you use a blue excitation light or a blue laser, the emitted light will be green, yellow, orange, or red. It cannot be violet. Similarly, when you are using red laser as an excitation source, the fluorochrome will be excited by the red light. The emitted light will be somewhere in the infrared region. It cannot be blue or violet or green or yellow or orange. Okay, this you need to understand. Okay, so now coming back to this question, which of the statement is false? I'm asking you a false statement regarding fluorescence. The excitation light is always of higher energy compared to emitted light. Correct? Correct, right? Which we saw. Excitation light should be of always of higher energy. This is right statement. Blue fluorescence can be produced, or blue fluorescent light or emitted light can be produced when a fluorochrome is excited with red laser. This is wrong. When you excite the fluorochrome with red laser, the emitted light will be definitely beyond red, that is infrared areas. It cannot be blue, violet, orange, green. It can't be. Okay, so this is a false statement. This is wrong. Third point, the emitted light is of longer wavelength compared to excitation light, which is true. Fourth point, the red fluorescence can be produced when a fluorochrome is excited by violet laser. This is possible. So this is correct. This is correct. This is correct. The false statement is this one. Okay. Now coming to the 15th question. See, the questions are arranged randomly for explanation purpose, because I've sorted this question on a concept basis, so that they may be a bit random. The brightness of a fluorochrome can be determined by all except. So you know what is extinction coefficient, what is quantum yield, what is stain index, what is spectral overlap. Let's see, but quickly revise it. So what is extinction coefficient is, it's a measure of the capacity of the fluorochrome to absorb light at a given wavelength. So when you are exciting a fluorochrome, say for example, we are using a blue laser. So the excitation light here is 488 nanometer. Now at this particular wavelength, if you are using a fluorochrome, how much amount of light it can absorb that? Okay, that capacity is called extinction coefficient. So extinction coefficient is the measure of the capacity of that fluorochrome to absorb light at a given wavelength. So when it is absorbing maximum light, as I said you, when it absorbs maximum light, it will emit maximum light. So it will be brighter. So fluorochromes which have high extinction coefficient will be always brighter. Okay, now coming, what is quantum yield? Quantum yield is defined as the ratio of the number of photons that is emitted for every photon getting absorbed. If when fluorochrome is absorbing 1 photon, if it is releasing 8 photons in turn, then the quantum yield is 8. In comparison, if you see another fluorochrome which is emitting just 4 photons for 1 photon absorbed, then the quantum yield is 4. So obviously the fluorochrome which is having a quantum yield of 8 will be brighter than the fluorochrome having a quantum yield of 4. Okay, so again quantum yield is also related to brightness. Higher the quantum yield, higher the brightness. Higher the extinction coefficient of a fluorochrome, higher the brightness. Okay. Now what is stain index? Stain index is something, the difference between the negative population and the positive population. This distance between the negative population and the positive population is called stain index. So basically we have a formula to calculate it, but the understanding is this. Say for example, if your negative signal is falling here and the positive signal is falling here, then it is very bright. For example, if you have a negative signal here and the positive signal is just lying next to it, then the stain index is very poor or low. Okay, so that is called stain index. So mostly flow cytometers discuss brightness in terms of stain index, and it is calculated by a formula like this. Okay, and we use it during titrating your antibodies. Okay, so now let's come back to the question. So the brightness of a fluorochrome can be determined by all except, of course, extinction coefficient. So higher the extinction coefficient, higher the brightness. So this is correct. Quantum yield, I said you. So if a fluorochrome has high quantum yield, then it is very bright. So this is correct. Third, stain index we discussed. Stain index is the distance between or the separation between the negative population and the positive population. So higher the stain index, more the brightness. So this is also correct. But spectral overlap has nothing to do with brightness of the fluorochrome. Okay, so spectral overlap, what is spectral overlap is? So this is the answer. This is nothing to do with brightness. What is spectral overlap is? Spectral overlap is when you are using 2 fluorochromes or multiple fluorochromes. Okay, some people confuse this with Stokes shift. Stokes shift is completely different. Stokes shift is something related to when you're talking about 1 fluorochrome, you can talk about Stokes shift. Spectral overlap comes into play when you're using more than 1 fluorochrome. So here I've just shown you a simple example, which is a 2 fluorochromes. So this is FITC, this is PE. Okay, now I'm just talking only about the emission spectrum, not excitation spectrum, only emission spectrum. So the emission spectrum of FITC or Alexa Fluor 488 is somewhere from 500 to 600. Okay, and similarly the emission spectrum of PE is somewhere between 550 to 700. But if you see, watch closely, there is some amount of light which is shared between both of them. Okay, FITC also gives some signal beyond 550 and PE also gives some signal from 550. So this can overlap. What happens? So because of this overlap, what happens? This is called spectral overlap. Okay, this overlapping between the emission spectrum of 2 fluorochromes is called as spectral overlap. This is called spectral overlapping. So the problem with the spectral overlap is some amount of this Alexa Fluor 488 signal will be taken up by the PE detector as PE signal, mistakenly taken in PE detector. Similarly, some amount of PE signal will be mistakenly taken in FITC or Alexa Fluor detector as signal. Okay, so because of this, we'll get some problems. This is called spectral overlap, and we need to correct this by thing called compensation, by a phenomenon called compensation. This is our next lecture, spectral overlap and compensation, which we will be discussing on the next lecture. Okay. Okay, fine. So then let's go for the next question. You have an instrument. Okay, now you need to assume you have an instrument with the blue laser 488 nanometer and a red laser 640 nanometer. Which of the fluorochrome you cannot use? Okay, now you have a blue laser line which will excite the fluorochromes at excitation maximum of 488 nanometer. Similarly, a red laser which will give you light of 640 nanometer. So if you have such a machine, you can excite all the fluorochromes which have an excitation maximum of 488 or 640 nanometer. Okay, now let's see what are the options given. FITC excitation maximum is 494. So 488, 494 is very close to 488. So you can use FITC. Second PE has excitation maximum 496, which is very close to 488. Again, you can use PE. Now coming to APC, excitation maximum is 650, which is very close to 640. Okay, so you can use APC. Coming to PERCP, which is pyridinal chlorophyll. So this excitation maximum is 482, which is close to 488. Again, you can use PERCP, which will be excited by the blue laser. Coming to Pacific blue, whose excitation maximum is 401. See now 401 is very far away from 488. Even its excitation spectrum will not come inside 401. Even the blue laser or the excitation spectrum of Pacific blue will not reach up to 488. So 488 is somewhere, 401 is way behind. Okay, so this can be excited by violet laser, which gives you a light of 405 nanometer, but not by blue laser. So Pacific blue will not be excited by this blue laser and red laser. Okay. Last option, Alexa Fluor 488, which can be excited by blue laser. Okay, so Alexa Fluor can also be, because 488 is very, again 488, it can be excited by blue laser. Okay, so the answer here is Pacific blue. Okay, Pacific blue cannot be excited by blue laser and red laser. It can be excited only by violet laser. Okay, any doubts? Any doubts? Clear now? So that's how you need to select your fluorochromes when you have a mission of one particular configuration. Okay. Now coming to the question 18. Which of the statement is false regarding fluorochrome selection? Check whether it will be excited by the laser of your flow cytometer. Correct. Okay. So when you are using a fluorochrome, it has to be excited by one of the lasers you are using. Check the stability of the fluorochrome by exposing, like this is crude, you can't do this. Third, check whether it will be detected in your fluorochrome flow. It will be detected in your flow cytometer instrument. Okay. So you should have a corresponding detector to capture the emitted light or emission maximum. Okay, so you should, if you use a fluorochrome, it is excited by a laser, but you don't have a detector to capture the emitted light, then it is useless. You can't use it. Okay, so you should have a detector in your flow cytometer to capture the emitted light. So we need to check this. Check whether it will be detected in your flow cytometer instrument. Fourth, check if there is an overlap with already existing fluorochrome. As I said, if you are using two fluorochromes where the emission is same, for example, FITC and Alexa Fluor 488, both have the same emission maximum, then you cannot use both of them. You need to select only one of them because you have only one detector for that emitted fluorochrome. You cannot, because since the emission maximum is same, you can use only one detector for that emission maximum. You can't use FITC and Alexa Fluor 488. You need to use any one of them. Okay, so if there is an overlap, then you need to select only one. So you need to check. You can't use in a panel both FITC and Alexa Fluor 488 in your panel. You need to select one among them when you are conjugating with the marker. Okay, so the answer is, false statement is, check the stability of the fluorochrome by exposing to light. This is the false statement. The next question, the advantage of using instruments capable of multiple fluorochrome or color detection. That is, what is the advantage? Simple is, what is the advantage of using a multiparametric flow cytometry? Okay, so this one I just discussed in the last class, right? So here is a 13 color instrument panel, and this is a 4 color instrument multiple myeloma panel. So both are multiple myeloma panel. This is a 13 color instrument panel, and this is a 4 color instrument panel. Okay, now these are the fluorochromes I will be using in the 13 color machine, and these are the markers to which it is conjugated. So it is kappa is conjugated to FITC, lambda is conjugated to PE, 56 is conjugated to ECD. So these are the markers, and these are the respective fluorochromes to which it is conjugated. Similarly, I have a 4 color panel. Since it is it's a 4 color instrument, I can use only 4 colors in this instrument. So this is a 13 color instrument, so I am using 13 colors. So what is the advantage of this over this? First advantage, as I said I can study any combinations in this 13 color. For example, I can study cytoplasmic kappa with CD19. I can study cytoplasmic kappa with CD28. I can study cytoplasmic kappa with 81. So any combination of markers I can study here. Whereas if I'm having only a 4-color flow cytometer where I have only 4 detectors are there, and I need to use a panel with only 4 markers, I cannot study the multiple combinations as I can do here. I can study combinations like kappa lambda, kappa 38, kappa 45. I cannot study kappa with 56. I cannot study kappa with 138. I cannot study kappa with 27. I cannot study kappa with 28. Similarly, 81, 117, 319. So I cannot study the combinations. So when you are not able to study the combinations, you cannot discriminate the populations easily, especially when the small population is very small. Okay, so that is the first disadvantage. Second disadvantage is coming to the volume of sample. Now, if this is a single tube, right? So only one tube is there. I'll drop all the 13 antibodies in this tube, and I can add just 100 microliter of sample to this, and then I can finish the job. So 100 microliter is enough to finish the entire experiment. But since in a 4-color instrument, I can only use 4 markers. Now I'm making 5 tubes here. So I need to drop 100 microliter in all the tubes. So now if I have a 4-color instrument, I need to use 500 microliter of bone marrow sample. Here 100 microliter is enough for me. See, this is fine. You may think, okay, 500, what's the problem? 2 ml of sample is there, so I can use 500 microliter. This 100 microliter is when the sample is hypocellular. Okay, 100 microliter may not be sufficient. Then I need to add 500 microliter here to get that desired number of cells. If it is 500 microliter here, now here 500, 500, 500, 500, 2.5 ml of blood will be needed, which may not be there in the marrow aspirate tube sample what sent to you. So here you have a problem here. So the second problem is volume of sample. When you use a 13-color instrument with 13-color panel, okay, the amount of volume of blood needed will be less because you are not using multiple tubes. Whereas if you use a 4-color instrument, since the tubes are more, to achieve that particular number of markers, the amount of sample you use will be more. 5 times in this example, what you use will be more than 5 times here. Okay, so that is the second problem. Third important problem is this one, antibody wastage. See, for 38 and 45 will be like your backbone markers, because 38 is your gating marker for plasma cells. See, here 38 and 45 is there only once, but since it's a gating marker, I need to add those markers in every tube, in all the 5 tubes. So my antibody consumption is more. Okay, so that is the third disadvantage. So you have 3 disadvantages when you are using a simple flow cytometry compared to a multicolor flow cytometry. Okay, so that was the question here. The advantage of using instruments capable of multiple fluorochrome or color detection, that is multiparametric flow cytometry, include all except populations can be studied across many combinations. Yeah, that is an advantage. Relatively less sample volume needed. Yes, that is an advantage. Third is less compensation and spectral overlap, which is wrong. I'll tell you. Fourth is less antibody consumption. That is correct. So the answer here is less compensation and spectral overlap. So we saw about the advantages of using multiparametric flow cytometry. Okay, where using multiple markers. The problem with using such multiple markers and fluorochromes in one tube is spectral overlapping, because since you're using multiple fluorochromes, the emitted light of this will fall there, that will fall here. So there will be a problem with spectral overlap, and you need to compensate it perfectly for good results. Okay, so when you're using multiparametric flow cytometry, the biggest problem is spectral overlap, which we'll be discussing in the next class. What I just showed you now, the emission spectrum of one fluorochrome will spill over into the other particular fluorochrome detector. So you will get fault signals and you need to correct it by compensation. Okay, so that is the answer for this question is less compensation and spectral overlap, which is basically not an advantage but a disadvantage with multiparametric flow cytometry. So which of the following is commonly used viability dye? See, commonly used viability dye in flow cytometry is 7AAD. Okay, acridine orange is not used in flow cytometry to my knowledge. We use it in MPQBC. DAPI, we don't use it in flow cytometry. We use it in fluorescent in situ hybridization. And this also we don't use commonly. So the answer is 7AAD. So coming to tandem, since many people have asked doubts, let's just finish off tandems. So what is a tandem fluorochrome? So let me go from the basics. Tandem fluorochrome are two fluorochromes that are closely associated. Okay, so it should be, first point is tandem fluorochromes are two fluorochromes that should be tightly bound to each other, closely associated. Okay, so what is the advantage? The emission spectrum of one. So for example, A, the emission spectrum of A, which is called the donor fluorochrome or the parent fluorochrome, should overlap with the excitation spectrum of the recipient fluorochrome. So I repeat, the two fluorochromes in tandem fluorochrome is nothing but two fluorochromes which are tightly bound to each other. One will act as a parent or donor, the other will act as a recipient. Okay, now the rule is the emission spectrum of parent or donor fluorochrome should overlap with excitation spectrum of the recipient fluorochrome. So this rule has to be satisfied for a tandem fluorochrome. Okay, so why this overlap should be there? If there is only if there is an overlap, there will be a fluorescent resonant energy transfer. Okay, there will be an energy transfer happening between A to B. Okay, so when a light is exciting A, it will not emit light. So normal fluorochromes, non-tandem, what happens? When excitation happens, excited light hits the fluorochrome, it goes for an excited state and then it emits light of lower energy and longer wavelength. But in case of tandem fluorochromes, what happens? The excitation light will hit the donor fluorochrome or the parent fluorochrome. Instead of giving emitted light from the parent, what it does, it just transfers its energy to the recipient. Now this energy is taken up by the recipient and it gives fluorescence as an emission. Okay, so this is the beauty of tandem fluorochrome. So energy transfer occurs, the resulting conjugate fluorochrome has excitation of that of donor or parent and the emission of that of recipient. Okay, so excitation will be that of the parent or the donor and emission will be that of the recipient. So that is the beauty of tandem fluorochrome. So this is an example where Texas red is bound to a parent fluorochrome or donor fluorochrome P. So here Texas red is the recipient fluorochrome and the donor fluorochrome or the parent fluorochrome is P. Now when we are using this tandem combination, which is called P Texas red or ECD, the excitation of this tandem will be the same as that of P, which is the blue laser 488 nanometer. But the emission light will be not that of P, it will be that of Texas red, which is 620 nanometer. Okay, so that is called tandem fluorochrome. So this is what? So you have, this is the excitation spectrum of donor fluorochrome or the parent fluorochrome, and this is the emission spectrum of the donor fluorochrome. Okay, this is the excitation of the recipient fluorochrome and this is the emission of the recipient fluorochrome. Okay, now for a tandem fluorochrome to function, you need to have this overlap. That is, the emission spectrum of the donor should overlap with the excitation spectrum or absorption spectrum of the recipient. Okay, then only the energy transfer will happen and you will get emission signal from the recipient fluorochrome. So again, I'm showing an example. This is a parent fluorochrome or the donor fluorochrome. So now this is excited by a blue laser, 488 nanometer, and the emitted light is orange. Okay, now I want to make a tandem dye. So I'm combining PE with Cy7. If you see Cy7, this is the recipient dye. If this Cy7 is not conjugated to PE and if you are using it individually, this will be excited by the orange light and the emitted light will be red in color. Okay, for example, in your machine you don't have an orange laser. Okay, now then you cannot use Cy7. Okay, so now you can use it by making this as a tandem. So I'm combining PE and Cy7. So this is what results. So when I'm using this, what happens? This tandem will be excited by the blue laser, same as that of the parent or the donor fluorochrome. But the emitted light will be that of Cy7, red color. Okay, so that is the beauty of using tandem dyes. So though you don't have an orange laser, now blue laser will excite this tandem fluorochrome and the emitted light will be different from that of PE. PE gives you orange signal or yellow signal, whereas this tandem fluorochrome PE Cy7 gives you a red signal, red light. Okay, so that is the beauty of using tandem. Okay, so many people have asked, what is the use of tandem? Why should I use tandem? Now let me give you an example. So I need to do a leukemia lymphoma assay. Okay, now but the instrument what you have is the best. You have a 4 laser instrument. Normally, market we have 3 laser instrument, blue, red, and violet. But let's, for example, we have a 4 laser instrument. We have a blue laser, red laser, violet laser, and UV laser. And we want to do a very complex leukemia lymphoma assays where you need to read multiple markers. Say, for example, in one tube, as we saw in myeloma, you want to do 13 markers in one go or 20 markers in one go. If you see in the market, what are all fluorochromes? Non-tandem fluorochromes, that is parent fluorochromes, okay, without tandem combinations. What are all available? Hardly you have only 7 fluorochromes available. So blue laser, non-tandem fluorochromes available is FITC, PERCP, and PE. Red non-tandem fluorochrome available is only APC. Violet non-tandem fluorochrome available is PB, KO, which is chrome orange and Pacific blue. UV, only one fluorochrome available is brilliant ultraviolet 395. Now I said you need to do leukemia lymphoma assay. Now your instrument is good. You have 4 laser instrument, but the number of fluorochromes to conjugate with the markers. See, for leukemia lymphoma, as I said, you need 20 markers or 15 markers or 10 markers, right? For example, you need all the markers for B, T, myeloid, so and so, right? So if you want me to name 19, 45, 10, 20, 22, 34, 10, CD117, 15, 13, 33, many markers are needed to characterize the blast. But though you have got a best instrument, the amount of fluorochrome options, non-tandem fluorochrome options available is just 7. So can you do the experiment? You can't do. There comes the use of tandem. Now, if you give me an option like you can use tandem fluorochromes. Now, if you open up that option of using tandem fluorochromes, now you see the number of colors or the number of fluorochrome options expands to 20. But how? See now, FITC, PERCP, PE, non-tandem fluorochromes. Since I can use tandem fluorochromes here, PE, Texas red, PE, P-Sci5, means this PC5, then PC7. APC, tandems of APC are where, see, the donor is APC, same APC, but if the recipient is different for both of them, APC 700, APC 750. Similarly, BV 421, I can use the non-tandem here. In addition to that, see the tandem numbers which has increased. BV 421, when it converted to a tandem dye, it becomes BV 570, BV 605, BV 650, BV 711, BV 786. See, all these fluorochromes, whatever this, see, if you take blue, all these fluorochromes can be excited by the blue laser because these 3 have same parent fluorochrome, which is PE. So PE can be excited by blue laser. So all these 3 can be excited by blue laser. Similarly, these 2 can be excited by red laser. These 5 can be excited by violet laser. These 4 can be excited by, or 3 can be excited by ultraviolet laser. So now the combination increased to 20. I can easily do my experiment. Now I can use 20 fluorochromes, so I can conjugate CD19 FITC, CD20 PERCP, CD45 PE, CD10 PE Texas red, CD73 PC5, CD13 PC7. So now I can conjugate different markers to different of these tandem fluorochromes, and I can do a easy experiment of multicolor flow cytometry. Whereas previously only 7 fluorochrome options were available, so doing a 16 color assay or a 20 color assay is not possible. So that is the advantage of using tandem fluorochromes. Okay, so tandem fluorochrome expand the number of colors that can be detected by a single laser source. Why? Because we are using the same parent for all the tandems, given that of one particular family. Okay, here P is the parent for PE Texas red, ECD, PC5, PC7. Here BV421 is the parent for, or the donor fluorochrome for BV570, BV605, 650, 711, and 786. Only the recipient changes for all these things. And since the recipient is changing, the emission will be changing for all these things. Okay. And very importantly, though the tandems are excited by the same laser of parent dye, it should have separate detector. Okay. Say you say like PE is excited by blue laser. So the PE tandems are also excited by blue laser. PE has a different detector. PE Texas red has a different detector. PC5 has a different detector. PC7 has a different detector. Then only you can collect 20 different signals. Otherwise you cannot. Okay. So this is the beauty of tandem dyes. Okay, so the same example. So this is the dotted one is the excitation spectrum of parent. The violet, yellow, and the other one all tandem dyes. You see the excitation is the same. Excitation spectrum or the excitation maximum is the same for all the 3 tandems, but the emission spectrum and emission maximum is different for 3 different fluorochromes, tandem fluorochromes. Okay, so hope now this is clear. Okay, now coming to this question, which of the following is a false statement about tandem dye? Donor and acceptor molecule should be in close proximity. Yes, they should be in close proximity. Expands fluorochrome options from a single laser source. Yes, it expands the fluorochrome options. Energy transfer between donor and the recipient is 100%. No, it's not always 100%. Some amount of energy may not be transferred to the recipient. So this is a false statement. Absorption spectrum of the acceptor must overlap with emission spectrum of the donor. Yes, true, it should be. So the answer here is false statement. So the third one is the answer. Okay, so which of the statement is incorrect regarding Stokes shift? So you know what is Stokes shift? Stokes shift is, see, don't confuse with spectral overlap. Spectral overlap comes into play when you're using more than one fluorochrome, more than two fluorochromes, two or more. Stokes shift is regarding one particular fluorochrome. That is the difference between the excitation maximum and the emission maximum, emission spectrum. Okay, or sorry. So excitation maximum and emission maximum. This difference is called Stokes shift. Okay, I repeat, it's a difference between the excitation maximum and the emission maximum. That is called Stokes shift. It is always better to use a fluorochrome with wider Stokes shift because the excitation light will not interfere with the emission light. Okay, because if you use very narrow Stokes shift as here, some amount of excitation light can be going inside the detector and will be interpreted as signal. Okay, so it's always better use a wider Stokes shift. Okay, now coming to this question, which of the statement is incorrect regarding Stokes shift? So false statement. It is the difference between the excitation peak maxima and emission peak maxima of wavelengths. Correct. This is the correct definition. Selecting a fluorochrome with longer Stokes shift is always better. Yes, correct. As I said, a longer Stokes shift is always better because if you do a narrow Stokes shift, the excitation light will be getting into the filter of that particular detector and it will give you a false signal. Instead of the emission giving signal, the excitation itself will give the signal. So that is a problem with narrow Stokes shift. So it's always better you select a fluorochrome with longer Stokes shift. Finally, Stokes shift of a fluorochrome is decreased when it is converted to a tandem dye. This is false. Whenever you are converting a fluorochrome, when you are making a tandem dye, the Stokes shift increases because you can make a tandem dye only from the donor or the parent fluorochrome, right? So when you are adding a recipient, the Stokes shift will increase because the difference between the excitation and the emission will increase when you are adding a tandem, when you are adding a recipient dye. So Stokes shift of a fluorochrome is always increased when it is converted to a tandem dye. Okay, so this is the right answer. So it is not decreased, it is increased. So this is the false statement. So which of the following statement is wrong? Brighter fluorochrome should be used with weak antigen. Correct. So this combination is correct. Tandem dyes with same parent or donor fluorochrome have different excitation spectra. No, have different excitation maxima. No. Tandem with same parent or donor fluorochrome by rule should have same excitation, right? It has to be excited by the same because the parent is the same. So the excitation peak or maxima should be same for all the tandem fluorochromes. So if it is APC 700, APC 750, the red laser can excite all these two tandems. Okay, the parent of these two is APC. So all the three fluorochromes will be excited by red laser. Tandem dye should not be subjected to high temperature or light due to the chance of dissociation. Yes, this is correct. Because tandem is coupled, two dyes coupled to each other. So when you expose it to high light and temperature, there is a chance like there is tandem dye dissociation. Two dyes can separate from each other. Weak fluorochrome shall be used with strong antigen. This is also correct. So the false statement here is this one. Okay. Third, how many cells or particles should pass through a laser beam at a given time? This is again rule of thumb, only one. Then only you will get correct signal. So most of you have got that right. In the pulse shown here, height and width is proportional to dash and dash of the cell respectively. So height is proportional to the fluorescent intensity and width is proportional to the cell size. Because longer the cell in the light beam because of its size, the width of the pulse will be more. And similarly, the intensity of the fluorescence will give you the height of the pulse. Okay, this one we saw it in the first class and also in the second class. So the answer is, so this respectively is there. So fluorescent intensity and size. Okay. Now this technique shown here is sorting, flow sorting. Okay, sorting same alike cells in tubes. This is called sorting.
થઈ ગયું
Okay,
હવે
now identify the population.
એના પછી છે લેમ્બ.
Excuse me.
આ તો શું હજી 8 ને 10 જ થાય છે તો આપણી પાસે ખાસો એવો.
So identify the population in the order of A, B, C, D. So A is a population which is having high side scatter and moderate forward scatter, which is neutrophils. B is a population which is having relatively higher side scatter than lymphocytes, but size greater than lymphocytes and neutrophils. This is monocytes. This is lymphocytes, which has very low forward scatter and low side scatter because it doesn't have granules. So this is lymphocytes. And finally, this population is debris and RBC fragments. So which of the below images shows hydrodynamic focusing? This is hydrodynamic focusing. Most of you got this right, so we're not discussing that. The purpose of sheath fluid is all for all the following except. So sheath fluid makes the cells to pass in single file. Yes, correct. That is one among the function of it. It increases fluorescent intensity. Sheath fluid has nothing to do with fluorescent intensity. So this is not the function of sheath fluid. This is wrong. Sheath fluid is used for internal cleaning and rinsing of the chamber. Yes, correct. It is something like rinsing what you do for your cell counters. And sheath fluid is used in transporting the sample from the sample tube to the flow cell. Yes, that is also correct. So because sheath fluid is the one which carries the sample. So that is also right. So the answer is increasing fluorescent intensity because sheath has nothing to do with fluorescence intensity. So the next one, the pink population here interpreted as, so this population is positive for HLA-DR and negative for TNF alpha. Okay, so this is x-axis, this is y-axis. So since this population is lying here, it is negative for x-axis marker and it is positive for y-axis marker. Okay, so it is positive for HLA-DR and negative for TNF alpha. Whereas the blue color population is negative for both TNF alpha and HLA-DR. And the sandal color population is positive for TNF alpha as well as HLA-DR. So it is double positive, it is double negative. Whereas the pink color population is positive only for HLA-DR and negative for TNF alpha. So last question, which of the plot is used for discriminating doublets? Okay, so this is a time plot which makes you to know whether the acquisition is stable. Okay, this is forward scatter side scatter plot which helps you to discriminate or eliminate the debris which can interpret with your analysis. This is your classic side scatter CD45 plot which will give you an idea about the lymphocyte, monocyte, neutrophil, basophil and other CD45 negative events, blast and so on. The plot which is useful to discriminate the doublet is this one, which is a plot drawn against forward scatter height and forward scatter area. So doublets will have higher area, okay, but same height. So in such way you can discriminate the singlets from doublets. Okay, so when you're going for subsequent analysis, you need to select only this population for further analysis. We saw this in the first class. Yes. Okay, so doublets, I repeat, doublets have higher area because two cells are struck each other, so they have higher area and higher width. Okay, whereas height will be same for singlets and doublets with respect to fluorescence. It will not vary much. So when you draw a plot against forward scatter height and area, you can discriminate the doublets from singlets, and you need to take only singlets for further analysis. So this is the plot which you need to use. Okay, so that comes to the completion of this particular assessment. As I said, everyone has done well. So this is the answer. So I just had a look of around some 35 people whose assessment. So some people have got 100%. Congratulations, Dr. Nima and Vijay Lakshmi, you have done very well. And most of you have done very well. I'm very happy about the progress. So if you have any doubts, we can go ahead and clear your doubts. Any doubts? Crystal clear? First 3 lectures crystal clear. So we'll be going for the second module or the second part of this course from next Friday, where we'll be seeing about spectral overlap and compensation, antibodies. Then how do we do processing? I show you a wet lab in that, how we process flow cytometry samples. Fourth will be analysis. So that completes the second part of this course. Third part will be full live analysis, like experiments, and how do you report. So any doubts? If there are no doubts, then we can conclude the session. So again, I congratulate everyone. People have done very well. Keep the same pace and try to learn. That is ultimate idea and goal behind this course. Okay then, bye, take care.